Before discussing any routing algorithm, let's talk about the graph abstraction, because we'll be using this graph abstraction to understand the working of a routing algorithm. So in this graph abstraction, we have a representation of graph G in terms of number of nodes and edges, where in our scenario, these nodes are representing set of routers. For example, this U, V, X, W, Y, Z, these are all routers, right? And then this E is basically representing the set of links between the different routers. For example, this link UV is connecting router U with router V. Okay, and similarly, this link between VX is connecting this router V with router X. This graph abstraction is, by the way, is very useful in understanding the working of routing algorithms, and is also useful to understand other network contexts. For example, in peer-to-peer networks, where the N is the number of peers and E is the set of the TCP connections between them, right? So here we'll take help of graph abstraction to understand the working of different routing algorithms. So you can see that each link has a cost associated with it, right? So this link between U and V has a cost of 2. So this cost could always be 1. So what do we mean by this? This means we are basically using hop count. Hop count means how many number of hops are there between a source and a destination, or it's inversely related to the bandwidth, or inversely related to the congestion in a link, right? So this cost can be assigned also manually as well, but usually this cost is taken as the hop count between source and the number of hops between the source and destination machines. So let's try to find the cost from router S to router Z. So say we want to go from router U to router Z. So what do you think? What's the cost here? So let's try to identify the cost here. Okay. So the cost to reach from U to Z depends upon which is the shortest path from U to Z. So what do you think? What is the least cost between U to Z? Right. So see how many number of neighbors are there for U. So we have a neighbor 1 here, V, then we have neighbor 2, X, then we have another neighbor that is directly connected with U, W, right? So we have 3 neighbors. So let's see which neighbor we have the least cost to reach the destination Z. So we can take this path from U to X, the cost is 1, X to Y, cost is 1, and then Y to Z, the cost is 2. So this is the cost of this. The cost of this link is 4. And similarly, if I look at this cost from U to W to Z, this is obviously the cost of this link, right? This is 10, and which is obviously more than 4. And what about this cost between U to X, then X to Y, and from then Y to W and W to Z? So obviously this cost is 8. Again, it's greater than, so the greater than this cost that we have calculated here, 4. So the least cost to reach from U to Z is 4. That is via use neighbor X. So if U has to forward data to Z, so obviously you will forward it via X, because via X it has the least cost to reach the destination Z, right? So let's talk about the first algorithm, first class of algorithms called link state routing algorithm. So as we have discussed earlier, that link state routing algorithms are global in nature. Means here every router have a complete topology complete information of the topology a router knows to reach all the other routers in the network, right? So the algorithm in this class that we'll be talking about is called Dijkstra algorithm. So we'll try to look at the working of Dijkstra algorithm with the help of example, and we'll also try to look at its algorithm. We'll solve an example, and we'll again look at the algorithm to understand its working. Okay, before we start discussing the Dijkstra algorithm, let's talk about the different notations that we'll be using in order to understand the Dijkstra algorithm. So first of all, this CXY is the cost to reach from X to Y. So it's the link cost to reach from node X to Y, right? And if Y is not the direct neighbor of X, so initially this cost would be infinity because we have no idea about the cost, so we will assume it. Infinity means it's not the direct neighbor. So if Y is the direct neighbor of X, so this cost is known, and if Y is not the direct neighbor of X, this cost is infinity to start with. Then look at this notation, which is dV. dV is the current cost to reach from source to destination V. So there is any source, and from that source, if I want to reach this destination V, the cost is dV, right? So it's the current value of the cost of the path from source to destination V. And PV is the cost. The next notation that we need to understand is PV, that is the predecessor node, the cost to reach the predecessor of destination V, right? So if I'm interested in knowing the cost to the predecessor node of destination V, that is represented by this notation PV. And here N is the set of nodes whose least cost path definitely known, right? So N is a set of nodes that includes all the nodes whose least cost path has been calculated using Dijkstra's algorithm, right? So in this Dijkstra the algorithm, the net topology or the link cost is known to all nodes. And how this is accomplished? For that, we send link state broadcasts. Means we broadcast the link state information. So all the nodes of the routers will be having the same information, right? So, so this means we have to compute least cost path from one node, say source, to all the other nodes, right? Even if I have to send data to a specific destination, I have to calculate the path to all the other nodes. It's iterative, and after k iterations, means after identifying the cost to reach all the destinations, this algorithm will converge. So let's see how it works. So let's try to look at the algorithm first. So it has two steps. It has an initialization phase here, and then there is a loop. We'll stay in this loop until we have identified the cost to reach all the nodes in the network, right? So initialization phase, let's assume that we have started this algorithm at router U. So this is the router that, or the node where we have initialized the algorithm. So in N, we have U. So the N, which is a set of the nodes that we have the cost, we have calculated the cost to reach to, contains U only. And for all the nodes V, for all of the nodes V, if V is adjacent to U, if V is the direct neighbor of U, then the dV, the cost to reach that node V, is the cost to reach from is equal to the cost to reach from U to V, right? So this is known. Why? Because V is the direct neighbor of U. And if this is not the case, then dV is infinity. So this is the initialization step here, right? So initially, N contains the node where we have started this algorithm. And for all the other nodes V, if V is adjacent to U, means is directly connected to U, is U's neighbor, then the dV is known can be calculated as the cost to reach from u to v, which is known, v being the direct neighbor of u. Else the cost is infinity, right? Is not known. Obviously, we will calculate it once we are in this loop. After this initialization step, so we enter into this loop, okay? And we try to find a node w not in n, such that the cost to reach that node w from u is minimum. So we try to identify many nodes in the network that we have not identified the cost to reach to. So then we'll add a node w in n such that the cost to reach from u to w is minimum. Okay, so we add w to n, and then we update the cost to reach all the destinations v from u using this formula. So what it says that the cost to reach destination v is either minimum of these two. Either it's the dv, which is the old cost or previously calculated cost, right? It's the old cost, whichever is the minimum, or is the cost to reach the node that we have just added into n plus the cost to reach from u to destination v, right? So either it's the old cost or it's the cost by adding the cost to reach the newly added node w and the cost to reach from w to destination v. So whichever is the minimum, will select it and will update the cost to reach destination v, and we'll keep doing this. Then we'll find another node that not in n, we'll add that node in n, and then we'll calculate dw for all the adjacent nodes to w, right? So let's try to look at an example, and then we'll come back to this this algorithm again. So here is the example, right? So we have this, we have this network topology here, right? And what we want to do is that we want to implement Dijkstra at u here, right? So these are the number of steps that we'll perform here. So at step 0, this is the initialization step, by the way. How many number of nodes are there in n? Only u, right? Remember, in initialization step, n contains only u, where we have started this algorithm, right? And what is the cost? What is the cost to reach dv? Yes, 2. Why? How do we know this cost? Yes, because v is the direct neighbor of u. Remember, in the initialization step, we said for all nodes v, for all nodes that are adjacent to u, the cost is known. Why? Because these are the neighbors of node u. But if these nodes are not neighbors of u, then this cost is infinity. We'll see how. So since v is the neighbor of u, the cost is known, right? The cost is from u to v, right? Being the direct neighbor. And what is the cost to reach w? Yes, w is also the direct neighbor of u. The cost to reach w is 5. And which one is the predecessor node? U itself, because w is the direct neighbor of u. And what is the cost to reach this x? Since x is also a direct neighbor of, yes, u. So that's why the cost to reach x is 1, right? And the predecessor node is u itself. So what do you think? What's the cost to reach this w in this initialization step? We don't know, right? Its cost is infinity. Why? Because y is not the direct neighbor of u, and similarly z is not the direct neighbor of u. So that's why the cost to reach y and z is infinity. So let me go back and look at this initialization step again. So in initialization step, means at step 0 on the next slide, n contains only U, right? Since we have started this algorithm at U. And for all the nodes, V is an adjacent node like, yes, like V in our example, X and W, this cost is known, right? So this cost can be calculated. And if it's not an adjacent node, the cost is infinity, which is true in the case of node Y and node Z. Okay, right. So in this initialization step 0, n contains only node U, and the cost to reach V is known, being direct neighbor of U, which is 2, and predecessor node is U itself, right? And similarly, the cost to reach node W is known, which is 5, and the predecessor node is U itself. Similarly, the cost to reach node X is 1, known. Why? Because X is also a direct neighbor of U. But the cost to reach Y and Z is not known because Y and Z are not the direct neighbors of or adjacent nodes of U. Right. So then we enter into this loop. Right. This is our first iteration here. So here we are in the loop of our algorithm, right? And the first iteration. So what we have to do in the first iteration, so we have to find a node W, or we have to find a node such that the cost to reach from U to that node is minimum, right? So we'll again go back to the algorithm and see what it says. So it says find a node W not in N such that the cost to reach that node is minimum, right? And we'll add it to N, and then we'll recalculate the cost to reach all other destinations. So we have, at the moment, we have cost to reach 3 nodes. So we have the cost to reach node B, we have the cost to reach node W, and we have the cost to reach node X. So what do you think, which node should be added into N? Yes, you're right. We will add X into N. Why? Because the cost to reach from U to X is minimum, right? Because the cost to reach to V is 2, the cost to reach to W is 5, and the cost to reach to X is 1, which is minimum. So we add X into N, our set, and then we calculate the cost to reach all of the destinations, right? So for example, we recalculate the cost to reach DW. So the DW, let's try to recalculate this cost, DW. So what will be DW? So DW will be minimum of the previous cost. What is the previous cost here? Just look at the previous step. What was the previous cost here? Yes, you're right, 5. So either it's 5, okay, or it is the cost to reach the newly added node. Yes, so the newly added node into N is X plus the cost to reach from X to W, right? So let's try to calculate this. So we'll take either minimum of the previous cost, which is 5, right? And the cost to reach X. What is the cost to reach to X? Yes, we know 1. And what is the cost to reach from X to W? What is the cost to reach from X to W? 3. How do we know it? Because W is the direct neighbor of X. So this cost is, since this W is the direct neighbor of X, so this cost is known 3. Right. So this means we will either take a minimum of 5 or 4. So what do you think? Yes. So we have a new least cost, 4. So what we have done here is we have updated the cost to reach destination W to 4, and now look at the predecessor node. So now if I want to reach from U to W, it will not be using this direct link because this is not the least cost path. So I'll be sending or be using link. I will be using this link U to X and then X to W because it has the least cost. Similarly, we will update our cost to reach y. So similarly here we can calculate, you know, dy. Again, it's the minimum of the previous cost. So what was the previous cost? Look at the step 0, infinity. Okay. And the cost to reach the newly added node, which is the node that we have added in step 1. Yes, dx. I mean, x has been added, the cost to reach x, and then the cost to reach from x to y. Okay, so we have to select minimum of either infinity, and the cost to reach to x is 1 plus the cost to reach to y from x is 1. How do we know this? Yes, because y is the direct neighbor of x here, so 1. So either we'll select minimum of infinity or 2. So which value is minimum? Yes, 2. So see, what we have done here is we have updated this cost since we have the new least cost 2, and the predecessor node now is, yes, x. And what about the cost to reach z? There's no change. Why? Because z is not the direct neighbor of the newly added node, the node that we have added into n. So the newly added node into n is x, and z is not the direct neighbor of x. Okay. So what do you think? Again, we are in this loop. Again, what we have to do is we have to find a node w not in n such that the cost to reach from u to that node is minimum, right? So, so what we should do now? So we have here. So we have here, either we can add v, or we can add y, because these two nodes have the same cost. V is the directly connected neighbor, so it will not make any difference. So let me we can add any node, by the way. So we'll add y here. So what we have done is we will add y into n. Why? Because the cost reached from u to y is minimum, which is 2. Okay, and yes, v is also 2, but you can add any node. So by adding v will not make any change in the table. So that's why I'm adding node y and see what changes it brings into the table. So again, so find a node w not in n such that the cost reach to that node, which is y in this case, is minimum from w. And then again, we have to calculate the path to reach all the destinations. Okay, so after adding y, let's again try to recalculate this path. All right, so I'll again calculate the cost to reach dw. So it's either minimum of the previous cost, which is what? Look at the previous step. Yes, 4, or the cost reach the newly added node. So which node I have added recently into n? Yes, you're right, y, and plus the cost reach from y to w, the destination whose cost I want to update. Okay, so 4. So it's minimum of 4. Or what is the cost to reach y? 2. Okay, and what is the cost to reach from y to w? Look at this. What is the cost to reach from y to w? 1. Why? Because how do we know this cost? How does y has this information? Because w is the adjacent node of y, means w is the direct neighbor of y. So cost is 1. So this means what? So we'll select either minimum of 4 or 3. So whichever is the minimum. So which is the minimum? Yes, 3. So now we have again updated the cost to reach w. But now this predecessor node is y. Now if you want to send data to w, it has to be routed through this path, means through y to w, because this contains the least cost now, right? And what about this cost here? The cost to reach z. Previously it was infinity, so again we can recalculate it. the cost to reach node Z. It's either minimum of the previous cost, which is what? Infinity, or the cost reached the newly added node, which is dy, plus the cost reached from the newly added node to the destination under consideration, which is Z. So it's minimum of either infinity, the cost reached to y we know is 2, plus the cost reached from y to Z being direct neighbor of y is 2. So either we will select infinity or we will select 4. Okay, so obviously we have selected 4 here. Okay, and the predecessor node is y now. Right, and again we'll try to find a node such that that node is not in n, and the cost reached from u to that node is minimum. So what do you think? Which node I should add? Yes, I should add. I should add v here. So now v has been added into n, and then we will again try to recalculate the cost to all the destinations. So if you try it, there won't be any change in the cost to reach any of the destinations. So again, I will try to find a node not in n such that the cost to reach from u to that node is minimum. So which node I should add now? Yes, you're right, w. So now I'll add w, and then again, I'll try to find a node that is not in n such that the cost to reach from u to that node is minimum. So that node is in this case. So I will add z into n. So at this point, the algorithm will converge, and we have all the routers. We have all the routers in n, right? So again, let's try to look at the algorithm here. So we have this initialization step where at the initialization step in n, initially we have router u, because at this router node we have started the algorithm, and for all the other nodes, if the other nodes are adjacent to u, the cost is known, which is true in the case of node v as per our example, which is true for the node v, x, and w, because v, x, and w are the adjacent nodes of u, or the neighbors of u, right? And if these if the nodes are not adjacent, means not directly connected with u, which is the case, which is true for y and z, then the cost initially, or in the initialization step, is infinity. Then we enter in a loop, and then we try to find a node not in n such that the cost to reach to that node from u is minimum. So we added x into n, and then we try to calculate the cost to all the other destination. And then again, we'll keep doing it. We'll keep finding nodes not in n such that the cost to reach from the node to that specific destination is minimum, and we'll try to update the cost to reach specific destinations. Okay, right?